Oh, hey, hello. This is lecture 3 of the spring 2025 computer vision class. I'm doing it recorded because I will be out of town on Monday, the January 13th, and again, Thursday, January 16th. That will be a separate lecture. So I hope you find this useful, and we'll get started. So this is background on linear algebra. Um, this is a very quick, condensed and summary introduction. We will not go into great detail, but we will refer back to a lot of these things frequently. So we're going to talk about points, about matrices and matrix operations, about eigenvalues and eigenvectors, about various types of matrix decompositions, and we'll look at NumPy throughout, or at least mention NumPy implementations throughout. And on NumPy, there's two packages, np.linearalg and np.algo. And I encourage you to explore those as we go. So again, these are severely condensed notes and will not go into great detail, but hopefully this is mostly, almost entirely review. Okay, and I'm going to be using a little bit of a cheat sheet. So let's start with points. A point is a location in n-dimensional space. So there's an example of a point. A point can be described by a tuple of scalars, x1 through nxn, relative to a given coordinate system. So it's very important to realize, for example, if that is x1, x2 in my coordinate system, then this might have the coordinate, say, 3, 5. And if I had a different coordinate system up here, it might have um, the coordinates minus, I'm making this up, -2, -4. So this same point can be described with different coordinates depending on the coordinate system, but it's actually the same point. So the Euclidean n space, Rn, is the set of all possible point locations together with the distance metric on the points. And the distance between 2 points in Rn, given a particular coordinate system, is the difference in each individual coordinate squared and taking the square root. So for example, if x is 3, 5, and y is -1, 7, then the distance between x and y is 3 minus -1 squared plus 5 minus 7 squared. Take the square root. And that is what? It's square root of 16 plus 4 equals the square root of 20. And one important point about this distance is it does not matter the coordinate system in which you draw it. The distance between 2 points is the same no matter whether your coordinate system's down here or over there. The distance measurement is the same. So vectors are used to describe point locations and directions. The geometric intent of what's meant by a vector will be determined by context. And so we can have a vector, we can draw the vector there. And you can think of these horizontal and vertical axes as vectors as well. So vectors have excuse me for a sec. Vectors have a length or magnitude, which is the sum of the squares of each components. When a vector is, or the square root of the sum of the squares of each component, and the square magnitude is just that sum of the squares. When a vector is multiplied by a scalar, the result has each component multiplied by a scalar. And so, for example, if this is a vector and we multiply it by 2, the effect is to scale it up by 2. And so there's a geometric intuition as well as a algebraic intuition, and that will be standard throughout. The sum of two vectors, x and y, is another vector formed by adding the components. And you can do this you can envision a picture as well of that. So if we have one vector here and another vector there, the addition of the vectors is achieved by taking this vector and adding it to there. And then the result of adding the components is that vector there. So this is x plus y. If this is x and this is y, that is x plus y. The dot or scalar product of two vectors is a scalar. It's written in many ways, but the one simple one is x dot y. And that is the sum of the component y's multiplication of each of the multiplication of each component in turn. And they're added up, and the result is a scalar. And we'll sometimes have to be careful of that. The cross product in 3 dimensions of two vectors is another vector. And it's a little funky to see, but if we have x1, x2, x3 is one vector, y1, y2, y3 is the other, then you get the first component by doing this cross multiplication, and that gives you x1 squared y3 minus x3 y1 y2. The second one is taking this third component and the first component, x3 y1 minus x2, or excuse me, x1 y3, and the third component is x1 y2 minus x2 y1. But the geometric interpretation is very important. We'll see if it picks it up here on the screen. But if I have two vectors represented by my pencil and my pen, then the resulting vector of the cross product is perpendicular to both of these vectors. This is the very important interpretation of the cross product. And of course, it would be a lot easier to do in class. But if those are the two vectors, this vector, it's perpendicular to both vectors. And so therefore, for example, if I have two vectors that define two directions, then the third direction is normal to the plane that's formed by these two directions. And again, these are intuitions we will get to as we progress. Let's see. So we write the magnitude of the vector is the same as taking the dot product and taking the square root of that. We'll also talk about the notion of a unit vector. A vector is a unit vector if its magnitude is 1. And we will typically write it by putting a little hat over top of it. And then a vector can be converted to a unit vector by simply dividing by its magnitude. And finally, we have the angle between two vectors. We have x here and y there. That is the angle between them. We'll describe as theta. And it's the cosine of that angle is the dot product, remember, which is a scalar, divided by the product of their magnitudes. And this gives the cosine. So in particular, if x dot y equals 0, which means x and y are perpendicular, then cosine theta equals 0, which implies theta equals pi over 2, or 90 degrees. And so we can determine if two vectors are perpendicular, parallel, or anti-parallel, which means they have opposite directions, by looking at the dot product. What did I mean to say here? Okay. By looking at the dot product, we can tell if they're perpendicular, parallel, or anti-parallel. So especially if they're unit vectors, if they're anti-parallel, then their dot product is -1. If they're parallel, their dot product is 1. And if they're perpendicular, the dot product is 0. So here's an important concept that we will make use of, and it's central to some advanced neural network algorithms we'll talk about, like transformers. Vectors can be projected onto each other. And in particular, if y is a unit vector, then the projection, this is x dot y hat times y hat, is the projection of x onto y hat. So let's take a look at what that means. So this is direction y hat. Let me write that a little more clearly. It's not much more clearly, but there it is. If that's y hat, and that is x, then this distance is x dot y hat. And so this is a vector. I'll draw just like that. The distance is x dot y hat. As a vector, it's x dot y hat times y hat. So that is the projection on, this is thought of as the projection onto, or let me say that again, it's the projection of x onto y hat. This distance here is x minus, or this vector here is x minus x times y hat, or x dot y hat times y hat. And then as an exercise, you can prove that x dot y hat is perpendicular to x minus x dot y hat, y hat. Okay, and you do this using the dot product and show that the dot product is 0. Okay, that's a quick little exercise. Now on to matrices. And so matrices, or a matrix, is a rectangular array of numbers with each number subscripted by two indices, ij, and so I is the row and j is the column. And you'll notice that in linear algebra, of course, the indices typically start with 1. In Python and most programming languages, the indices start with 0. In MATLAB, they actually do start with 1, or at least last I knew. We can write it, this is a shorthand, capital A, which is the matrix, and the parentheses xij, or a sub ij, and then you just need to know the dimensions of the array. So we write the dimensions of the array as m times n, for m rows and n columns. And then just for notation, we'll tend to use capital letters, bold-faced, for matrices. In particular, the m times n identity matrix denoted by I sub n is the matrix such as a square matrix where the values are the Kronecker delta, basically where I equals j. So where the row and column are the same, we get a value of 1, and otherwise we get a value of 0. So we have is I3. So algebraically, we're typically going to treat vectors as column vectors. So if we have we are going to think of, typically we'll think of these as the column vectors. And similarly, we'll think of these as the row vectors. But generally, vectors will be treated as a column vectors of an m by 1 array matrix instead of row vectors. This is a little bit contrasted to what's in NumPy. NumPy looks like the row vectors, but in most cases you can treat them interchangeably without too much trouble. But be very conscious of this. But the convention in most linear algebra work is to think of column vectors. A vector is a column vector. So the transpose of a matrix, written with this, what looks like a kappa superscript T, but it's actually not a T, is just the interchanging of rows and columns. So if I have 1, 3, 6, 2, 4, minus 5 is my matrix, that is matrix A, then A transpose equals 1, 3, 6, 2, 4, minus 5. And so the A is 3 by 2, and A transpose is 2 by 3. And clearly, the transpose of the transpose gives us the matrix back. And then when A transpose is equal to A, then A is said to be symmetric. So for example, if it's 1, 7 minus 3, 2, 4, 0, then it would be 0 minus 3, 7. So this matrix is symmetric because I didn't want to do that. I wanted to do that. These are the same, and it's also true for these. And of course, a symmetric matrix can only be square. And to reinforce a little bit what I was talking about earlier, or just a minute ago, when X is, we typically write a column vector in this way, and if we want to write it as a row vector, we put the transpose on it. So if for a vector X, we treat it as a column vector, and then if we want to treat it as a row vector, we write X transpose. And that is a convention I will typically follow. So addition and multiplication are standard operations. The sum of two matrices is just the sum of the component-wise indices. The product of a constant with a matrix is the constant times each of the components of the matrix. And notice we can write it both on the left and on the right. And so matrix multiplication by a constant is commutative, and we will use this property. The product of an m by n matrix with an n by p matrix is an n by p matrix. So we take the first component and the last component, or the second component, and the middle components have to be the same. So just to illustrate, to draw this, now let me if that's our matrix A, and B is that, then A times B is 3 times 3 and minus 1 times minus 2, 1 and 4. So that's minus 7. Then 3 and 3 and minus 1, that's 8. 5 and 2, 5 times minus 1 is minus 5, plus 8 is 3. So we have 20, and 4 we have, what's that? That's 32. And minus 12 and 7 is minus 5. So that's AB. So in pictures, the way we do it is we have the rows times the columns. And you have to have the same number of rows in A as columns in B. So there's some basic operations, basic properties. Matrix multiplication distributes over addition, matrix addition. And of course, you have to be very careful of appropriate size matrices. You can't add or multiply matrices that don't line up in terms of dimensions. And I should have said this earlier. The notion of multiplication in linear algebra here is actually the notion of a dot product in NumPy. And that is actually consistent with the NumPy or the dot product we've already talked about here today. One hint, whenever doing matrix multiplication as part of a larger set of manipulations, use the fact that the numbers of rows and columns in the first matrix, or the number of columns in the first matrix, must equal the number of rows in the second, as a check on compatibility. And it's a sanity check to make sure you've actually done your math right. Okay, so there's several facts that we need to know. The dot product is equal to a matrix multiplication, and that dot product or matrix multiplication in the case of vectors only is commutative. So for example, and V equals V1, V2, so Vn. We're thinking of these as n by 1 arrays, then U dot V is UIVI. It's the same as U transpose V, which is the same as V transpose U. There's one caveat that you have to be super careful of in implementation is these technically, these are 1 by 1 arrays, whereas this is a scalar. Okay. The other thing is an outer product of a vector and another vector, and they don't actually have to be the same dimensions, is an n by n array. So let me write that out a little bit, and I'll change colors just to keep it separate. That's U. V transpose is V1, V2, Vn. And if you work through just the numerics, you have U1, which is the only component in the row, multiplied by V1, multiplied by V2, multiplied all the way through Vn. So this is U11 or U1V1, U1V2, all the way up to U1VN. Oops. And then it starts again, U2V1, U2V2, all the way up to U2VN. And the last component of that is UNV1, UNV2, all the way up to UNVN. Let's see, did I get that right? This is UMVN. Okay, so very, very important, simple matrix. This is one of those cases where the visual distance between two things does not match up with the mathematical distance. So this is U V2 U, and so this is a 1 by 1, and this is an m times n. So this is called the outer product. And I guess it's important to note that the transpose has the higher precedence here. So if you wanted to have transpose applied after multiplication, you would put a parentheses around the u and the v, but then of course the dimensions wouldn't match up. Another thing to note, and this is pretty obvious from what we've been talking about, is the squared magnitude of a vector x is can be written as X transpose X, as long, again, as you interpret the fact that this is really, in some strict sense, a 1-by-1 array. And this comes up when you do the mathematics of this. You actually have to pull it at the scalar value out. A fact that we will make use of fairly frequently, or a interpretation that we will make use of fairly frequently, is this. If we write A instead as column or row vectors, then if we multiply by B, so we have AB, then that is the multiplication of the matrix A by the vector V is A1 transpose by B, A2 transpose B, all the way up to AM transpose B. So in other words, if we write these out as row vectors, we write the matrix out as row vectors, which we need the transpose for to be consistent with our notation. Then when we multiply it by B, it's the dot product all the way straight down, or the A sub I transpose times B. So A1 transpose B, A2 transpose B, all the way up through AM transpose B. Matrix can be multiplied in block form. This is not something we're going to spend too much time on, so I'll just let you have a look at that. Trace and determinant. So these are pretty important operations overall in terms of matrix algebra. So the trace of a matrix is the sum of the elements along its main diagonal. And so these are only applied to square matrices. Traces and determinants only are applied to square matrices. So the trace of a matrix is the sum of the elements on the main diagonal. So let's do 3, 6, minus 1, 4, 7, 3, minus 2, 5, and 1. So then the trace is just 3 plus 7 plus 1, which is 11. It seems rather arbitrary, but there tends to be a very important component of our notion of what's going on with that main diagonal. Determinant of the matrix is written det A, or sometimes it looks like single line, capital A, single line. So this can be defined recursively. When n equals 1, the determinant is just the component. When n equals 2, the determinant looks like what we use for the cross product. So we have A11, A12, A21, A22. The determinant is this, the diagonal, product of the diagonal minus the product of the off diagonal. So A1, A22 minus A12, A21. For n greater than, stick strictly this, well, it works for greater than or equal to 2, but let's make it greater than just for clarity. What we do, M sub ij is the submatrix of size 1 dimension smaller, obtained by deleting row I and column j. So in our example above, M11 equals 7, 3, 5, and 1. And the way this works, you can choose any row or column of A, but so let's choose any row of A. Then the determinant of A is the summation over each component of that row, of the row value times the determinant of this M matrix. And then the trick is whether or not it's a positive sign or a negative sign. But we can just write this out fairly easily just to see. So with this, it's 3 times the determinant of 7, 3, 5, 1. So that is obtained by combining 3 with this submatrix. And again, you have I in that upper left corner, you have I is 1 and J is 1. So that's minus 1 squared. And so that's positive. And then it's minus 6 times the determinant of 4, 2, 3, 1. And then it's minus 1 times the determinant of 4. Oh, this should be minus 2, 7, and 5. And you can press through that to figure this out. But the determinant, or to practice, the determinant has some beautiful properties. The determinant of an identity matrix is just 1, which is pretty clear. A little bit harder to show is the determinant of a product is the product of the determinants. Somewhat easier, just algebraically, is the determinant of the transpose is equal to the determinant of the matrix. But this is the superstar property, because even though matrix multiplication is not commutative, the determinant computation is commutative by virtue of this property, and then you can manipulate the matrix multiplication in many ways. So then we have another very important property called the inverse. Again, this should be review, but it's basically if A and B are matrices, and at this point we're not going to make them square, but if they're matrices such that A, B equals I, then A is said to be the right inverse of A, and if there's another matrix C such that CI is the identity, then C is the left inverse of A. So for square matrices, we have this very important property of the left and right inverse if they exist. The left inverse and the right inverse, or the left inverse exists if and only if the right inverse exists. And in this case, they're equal, and A is said to be invertible. So let's look at a few properties of this. Let me give you an example first of non-square matrices where we have an inverse. So let's make A equals 1, 1, 0, B equals 0, 1, or 0, 2, 1. And I did this in advance so that I didn't have to try to make something up on the spot. B equals 5 sixths minus 2 sixths, 1 sixth. Make sure I got that right. 3 sixths minus 2 sixths, 2 sixths. Let's see if that actually works. So the first row of B, A times the first column of B is equal to 1. The first row of A, this is a 2 here, I think. The first row of A times the second column of B is minus 2, 6 plus 2, 6, so that's 0. This second row of A times the second row of A times the first column of B is 2, 6 minus 2, 6, so that's 0. And the last row times the last column, we have a 0 there, 2, 6, so that's 4 sixths. and a 1 there, so that's also 1. So back to our square matrix, friends. A matrix that is not invertible, a square matrix, is called singular. And so here are very important properties. A matrix is invertible if and only if the determinant of the matrix is non-zero. If A and B are both square matrices and both invertible, then the inverse of the product equals the product of the inverses. The determinant of the inverse is the inverse of the determinant. And this is fairly easily proved because we know that the determinant of the identity equals 1, and the identity equals A times A inverse. So the determinant of the identity equals the determinant of A times A inverse. But we know that the product of the determinants or the determinant of the product is the product of the determinants. And so you get, by dividing, you get the determinant of A inverse equals 1 over the determinant of A. So that is a very important property of determinants. The determinant of the inverse is the inverse of the determinants. And we use this property 36 here that to get this fairly simple answer. And we get we use the factorization of the determinants to get this. Did I get all of that? So we're not going to talk about how to compute inverses, but you can see for a 2 by 2 matrix, you get the inverse is to reorder the diagonal. The off diagonal is the minus the diagonal of the original off diagonal and divide by the determinant. Okay, so special forms of square matrices. A diagonal matrix A is a square matrix where the off diagonal values are 0. So here's a simple example: 3, 5, minus 7, 0, 0, 0, 0, 0, 0. That's a diagonal. So a lower triangular matrix has Aij equals 0 whenever the row is less than the column. So this would be 6, 8, 1, 3, 5, 2, 0, 0, 0. That's a lower triangular matrix. An upper triangular matrix could be the transpose of that. Nice properties of products of diagonal matrices are diagonal. It's pretty easy to prove. And so in particular, the product of an upper triangular and the product of a triangular matrix, a lower triangular or upper triangular and lower triangular. Boy, that's a mouthful. Okay. So for determinants are very easily calculated for triangular matrices, and for diagonal matrices, it's just the product of the terms on the main diagonal. And so in particular, if you have a zero on the main diagonal, the determinant is zero, and it's a singular matrix. So a square matrix has this easily proven property that if a matrix is what's called orthogonal, if its inverse equals its transpose. And that's a definition, I'm sorry, not a proof. So the matrix is called orthogonal if its inverse equals its transpose. And it's this is what I meant to talk about showing. It's very easy to show that orthogonal matrices have determinants that either 1 or -1. And this is similar to what we just showed, except we also have the property, make use of the property that the determinant doesn't change when you transpose the matrix. So we also have this very nice property that when the determinant is 1 and all the entries in the matrix are real numbers, it's called a rotation matrix for reasons that will become clear as we proceed. Not quite ready for that yet, but we'll get there in just a few minutes. Eigenvectors and eigenvalues are crucial. We'll make use of them a lot. Eigen is just the German word for same. So the vector x is an eigenvalue of a square matrix A, and the scalar lambda is an eigenvalue of A if A times x equals lambda of x. So this is a pretty, when you think about it, it is a pretty intense property. So what we've got is we've got this m squared values in A. We've got a vector v or a vector x, and we multiply the n squared value by x, and we're guaranteed to get back x with just a scalar multiple. And we will show that we will make a use of this and try to understand this quite a bit. So the other way to look at eigenvalues and eigenvectors is to look at this property. So if we have a x equals lambda x, then we have a minus lambda x equals 0. And here's a little trick. Think about that. So what we've inserted is an n by n identity matrix. So we've just used the fact that Ix okay, so let me erase this and start over. Nothing new, just want to make sure it's clear. So we have Ax equals lambda x. So we have Ax minus lambda x equals 0. Now we slip a nice little trick. We can put in the identity matrix because the identity times any vector is that vector back. And now we can factor. And one of the properties I haven't shown you is that if a matrix times a vector is zero, either the matrix is singular or x is zero. And so in particular, we know, and actually that's fairly easy to prove because if it's non-singular, then it has an inverse, and the inverse will get rid of that, and x will be zero. So what this tells us, since a, in this case, a has to be singular, we know that the determinant of a minus lambda times the identity is zero. So what this is called is the characteristic equation. And what we get is x is an eigenvector of a, not x. I can't believe I didn't caught that before. If x is in the null space of a minus lambda I. So null space is the set of vectors that gets mapped to zero. And then we talk about the rank of an n times n square matrix as the number of non-zero eigenvalues. And if the rank is less than n, it is rank deficient and singular. And there's some technicalities here. An eigenvalue may appear multiple roots of the characteristic equation, in which case it is counted multiple times as a non-zero eigenvalue. Okay, let's keep going. Let's take a look at an example, which is a rotation matrix in 3 dimensions. So this is a rotation matrix in 3 dimensions. And in fact, you can easily check that its determinant is 1, and its transpose is an inverse, which means it is orthogonal. So if you're practicing this, you can show fairly easily that its determinant is 1 because you just pick the left third row and you only have to look at this last column, and cosine squared plus sine squared is 1. And it's transposed in its inverse. If we look at the matrix and look at its eigenvalues, we have 2 real eigenvalues and 2 complex eigenvalues. So the real eigenvalue is 1, which is really easy to prove. And the complex eigenvalues, which always come in conjugate pairs, which means we add or subtract the imaginary component, is e to the I theta, or thought of another way is cosine theta plus or minus I sine theta. And in particular, when we look at the eigenvectors, the eigenvector corresponding to the real eigenvalue is 0, 0, 1, which is very easy to see. We just take this and multiply by 0, 0, 1, and we get 0, 0, 1 back. And so we get, if this is x, we get x back, which means lambda is 1. But the cool thing about it is we have cosine theta plus, we get the complex eigenvalues, and they encode the axis, the angle of rotation. Okay, so if we think about eigen means same, and points along this eigenvector that, and this actually applies to arbitrary rotations in 3D. the real eigenvalue of 0, 0, 1 is the eigenvector corresponding to, well, I'm sorry, let me rephrase that. The eigenvector corresponding to the real eigenvalue is 0, 0, 1, which is the z-axis. It's actually the axis of rotation. And if you think about it for a little bit, points along this axis are unchanged by the rotation and therefore fixed points of the rotation. So if you have a rotation in 3D, and I don't know whether you can see my, oh, maybe this can see. If you spin around and you rotate, everything out here is rotating around, but points along my pen, which is the axis of rotation, right along the axis of rotation, that infinitesimally thin line or axis don't change. Everything else rotates around there by this angle theta. And of course, if you haven't seen this, this is a very important formula in mathematics. E to the I theta equals cosine theta plus or minus I sine theta. And just for fun, what happens when theta is equal to pi? What you get is e to the I pi equals the cosine theta is -1, sine theta is 0. And so if you combine those, you get e to the I pi plus 1 equals 0. And so you have the 5 most important quantity in math. Or nature even, related in a single equation. It's called Euler's equation. Some people call it God's equation. It is amazing. And you can prove this by simply computing the Taylor series expansion of each of these quantities. And you'll see that the Taylor series expansion of e to the I theta is equal to the sum of those two Taylor series expansions. And you get this beautiful result. Back to rotations in 3D, they all have the same structure. That is, there are two complex eigenvalues that give the angle of rotation through this cosine sine formula, and the real eigenvalue, which is always 1, and its associated axis is the axis of angle, and its association eigenvector is the axis of rotation. So again, two complex eigenvalues give the axis of the angle of rotation, and we can ignore the eigenvector. The real eigenvector is always 1, and its associated eigenvalue is always 1, and the eigenvector associated with it is the axis of rotation. And we'll come back to this. The properties of eigenvectors and eigenvalues. So here's a cool one. Any matrix, square matrix A, the sum of the eigenvalues is the trace, and the product of the eigenvalues is the determinant. For a triangular matrix, you can read the eigenvalues straight off of the diagonal elements. No calculations necessary. You can just read them as they go. If I have two matrices, A and A squared, they have the same eigenvectors. And if x lambda is an eigenvalue of A, then lambda squared is an eigenvalue of A squared. And this one's pretty easy to prove with the products, properties of determinants. If A equals M inverse B times M, For an invertible matrix M, then A and B have the same eigenvalues, but not the same eigenvectors. So that'll probably show up on the practice problems, just to make sure you're with us. So because we require solving higher order equations, there's computing the eigenvectors and eigenvalues is a numerical problem. And we won't worry about that too much. And so in particular, what you're going to use is np.linalg.eigen of A. And if this result is B, then B0 is a 1D array of eigenvalues. B1 is a 2D array, and its columns are the eigenvectors. Okay, so that's something to remember. All right, one more next thing. What happens when we have a symmetric matrix? So we have a very important property. The eigenvalues of symmetric matrices are all real. They're not necessarily positive, but they're all real. And we have this next very important property is the eigenvectors corresponding to distinct eigenvalues. This doesn't hold quite so easily if you have repeated eigenvalues, but most packages will give you back orthogonal vectors. So anyway, if the eigenvalues are all distinct, then the eigenvectors of a symmetric matrix are orthogonal. And any symmetric matrix A can be written as this form V D times V transpose, or this summation, and that I'll explain in a minute. So any symmetric matrix can be written this way, and this is called a symmetric or spectral or eigenvalue decomposition. So it's a spectral or eigenvalue decomposition, and it is an extremely important decomposition. So let's write this out as A equals V D V transpose. V equals V1 V2 Vn. These are orthogonal to each other. And they're unit vectors. We can also write these out with the same values of V as lambda 1. Oh, I'm sorry, I skipped over one part. D equals lambda 1, lambda 2, lambda n, and then we have zeros off the diagonals. Okay, so D is a diagonal matrix, and this is one simple notational thing, so you don't have to keep writing out all the zeros. You make a big zero here and a big zero there. So we also have this formula that A equals the sum of lambda I VI, oops, except I should make that a unit vector, VI transpose. And so VI equals VI1, VI2, VIN. And so this is an n by n outer product. Remember back to outer products earlier in the class. And we can do this n over n. So we form all these n by n matrices here, and we multiply them by the eigenvalue and we sum them up. So we don't do this much in practice, but we do make use of this property as we go. So the next decomposition is a singular value decomposition. And this one has very important properties. If we have any matrix m times n, and it's not necessarily square and it has real values, it doesn't have to be square or symmetric. It can be written as an orthonormal matrix A or U, a list of positive entries, and V is also, but V is m n times n, and it also contains orthonormal columns. And this is unique. So what does this really mean and look like? So U is U1 these columns V, and there's M. And S looks like and in particular, if M is greater than N, said one thing and wrote another. If M is greater than N, then I get then S equals this. If I did that backwards, get that straightened out here. So you have M minus N zeros. Okay. So you'll see this defined. Well, let me just stop for a second and reemphasize this point here. So we have A is U S V transpose. Now, if A is symmetric, and its eigenvalues are positive, are non-negative anyway, then when we write A equals, what do we use in notation wise? Then we have V equals S, V equals U, and D equals S. Let's call this 1, and this 2. Okay. So this is if A has this very strict property that it's symmetric and its eigenvalues are non-negative, then the spectral decomposition and the singular value decomposition are the same. But the singular value decomposition is much more general. The matrix only has to have real values. It does not have to be square. And the results are the singular values are all non-negative. They could be zero, but they're all non-negative. It's an amazing property, and it's a very impressive proof. Okay. I'm going to stop this recording and take a break for a minute, and then I'll come back.